Now we want to talk about some of the quantitative descriptions of the energy of phase changes. So if we think about processes like heating up water, we're going from say negative 20 degrees Celsius to 50 degrees Celsius. We know that there's going to be some energy required to change the temperature, right? We would start, we go negative 20, that's solid ice. We would warm it up to say 0 degrees Celsius. That's where we get to melting. And as we put in heat, the temperature goes up. But once we hit 0 degrees Celsius, that's the melting point, or where we start to undergo fusion is the technical term for melting. You are now putting in more energy, but that energy is not going towards increasing the temperature. It is all going towards melting the ice. So this graph that I have where it's this slope up, you can see energy is in the horizontal and temperature is on the vertical. You put in more energy. If the phase is the same, we know the temperature goes up. Once you hit a phase change, you're putting in more energy without the temperature going up. So whenever you are heating a substance and potentially undergoing phase changes, there are going to be two different types of processes, and they add together. Remember, energy is a state function, enthalpy is a state function, so these sorts of heats going in, we have different kind of parts of the path of changing the temperature, of putting in this energy, and we can deal with each part independently. When we're dealing with heating a substance, when we're looking at changing the temperature, the equation that we're always going to be using is Q is equal to mc delta T. M is the mass of the substance, C is the specific heat capacity, and delta T is the change in temperature, where it's always going to be final minus initial. So when we're looking at this, if you're dealing with a substance, this specific heat capacity is a property of the substance. So if you're looking at water, you can look up what the specific heat capacity of water is. The mass does depend on how much you're dealing with, and the delta T does depend on the change that you are doing. So that would be something that is unique to your system, but C is always going to be, you're always going to be able to look that up for whatever it is. You can just Google water specific heat capacity. And so that's always what we're looking at. Well, no, that is, does not correspond to changes in phase. You always have to be dealing with one substance. Different phases, solid, liquid, and gas, water, all have different heat capacities that you would need to deal with differently. When you undergo a phase change, the temperature no longer changes. You will note that over here, there is no temperature in there. Instead, the heat is equal to some amount multiplied by a delta H value, the enthalpy of that process. So this is going to be similar to doing stoichiometry, doing a process where you're dealing with what's the delta H of the process. It's either going to be in kilojoules per mole, in which case your amount needs to be in moles, or in kilojoules per gram, in which case your amount needs to be in grams. So your unit needs to match. Both of these are going to show up, and you're going to have the delta H values that are also provided. So let's look at an example of just kind of one part here. The enthalpy of vaporization of methanol is 35.2 kilojoules per mole. How much heat is required to boil 209 grams of methanol?
Okay, so how much heat is required to boil? So whenever we're looking at energies for phase changes like this, we're not going to worry about temperature. What we are going to worry about is some sort of enthalpy, right? That's going to be our delta H. And we can see that the units on that delta H are in kilojoules per mole. And so it's going to be a relationship. It's going to let us relate an amount of, in this case, methanol that's undergoing boiling and the heat that is then associated with that. Okay? And so we know we're starting out, we have 209 grams of methanol. And so that's not going to work to correspond with kilojoules per mole. So what we're going to have to do is turn that into moles. And so we're going to need to calculate molar mass. Calculating molar mass is going to be based on the atoms in our molecule. So I have 1 carbon plus 4 hydrogens plus 1 oxygen. And then I need to know the mass of each type of atom. And I find those on the periodic table. Those are the mass values that are on the periodic table. Carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 16.00 grams per mole. For me personally, I just prefer using 2 digits after the decimal point everywhere when I'm calculating molar masses. The reason for that is it keeps it consistent. I know at the end of when I'm done putting everything together, I'm going to have 2 digits after the decimal point for my correct sig figs. If you want to use more, that's fine. You can't use less, in case there are actually some atoms that don't have significant digits after that lead. I use at least 2 digits after this point. If you want to use more, that's fine. It does not matter. I think it's just a little bit easier, a little bit cleaner. These come together to give me 32.05 grams per mole. So that's the molar mass of my entire molecule, CH3OH methanol. So if I want to use that now, I have my 209 grams of methanol. My molar mass is 32.05 grams per mole. Okay, so this I can see these units are a ratio. And so what this tells me is this is the mass of 1 mole. So I have 32.05 grams per 1 mole of CH3OH. We don't write the 1 on the mole, but whenever it's per something, there's always an implied 1 on that. And that number right there is exact. It has an infinite number of sig figs because it is exactly 1 mole of CH3OH has a mass of approximately 32.05, or a rounded or an inexact mass of 32.05. So this would have 4 sig figs. That has infinite. We just don't worry about its sig figs. So we've canceled out our grams. If we evaluated this, this would give us the moles of methanol that we have. But instead, what we'll do is we're just going to multiply it by my delta H value of 35.2 kilojoules per mole. So per mole tells me again, that's per 1 mole of CH3OH, 35.2 kilojoules. The moles cancel out. And overall, I get 229 kilojoules. This is how I do unit conversions. You do not have to do unit conversions in this way. Whatever works for you is fine, as long as you are demonstrating that you are using conversion factors, you are using the correct conversion factors. If you like train tracks, lines, whatever, if you want to show compute intermediates, I'm doing it all in one go. You can calculate an intermediate value and then convert that value. Whatever works for you, I just need to show that you're conveying kind of the thought process and the method that you're doing. The other thing that I want to talk about here is we've calculated how much heat is required to boil. We've gotten a number out of this, but we want to be mindful of the fact that there is some different language. This is boil, and that is vaporization. So we want to think about, is this really what's going on? So vaporization means liquid to gas. Okay, so that is the same thing as boiling. So that means that the sign of this heat of vaporization does coincide with this. So if you want to boil this methanol, you will put in 22.9 kilojoules because it's endothermic. If you were to condense, which would be gas to liquid, it would be negative 229 kilojoules. Where that negative sign comes from the fact that heat would be leaving the methanol. We're not asking about that here, but we want to be mindful. Generally, you're always given enthalpy of vaporization. It will always have a positive sign. But you can use that, the exact same calculation, you just throw in a negative sign right there and get the negative number if you're doing the opposite. So you're always presented enthalpy of vaporization as a positive number. You should be mindful of the fact that you can switch the sign on that value.
Participation 9.1, question 1. The enthalpy of vaporization of water is 2.24 joules per gram. What is the heat associated with the condensation of 23 grams of water? This is the first question on participation 9.1 due Tuesday, September 1st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, the enthalpy of vaporization of water is 2.24 joules per gram. What is the heat associated with the condensation of 23 grams H2O? All right, so if we return to our heating curve, this is the curve that shows us whenever we're heating something up, what it kind of goes through. And we can see there's these different parts. So we've looked at kind of these phase changes where we know there is no temperature change, we're just putting heat in. The technical term for this, or the kind of fancy term, is latent heat. So latent means hidden, so it's hidden heat. This is extra heat that you have to put in or comes out from a phase change that does not change the temperature of the substance that that's undergoing the phase change. It's important to note that that energy has to come from somewhere and it can affect the surroundings. So for example, you'll note this curve is relatively accurate. You'll note this is a pretty narrow distance for this would be melting a solid or say undergoing fusion, or the reverse would be freezing. And then in the opposite, you can see a much longer line that corresponds to going from liquid to gas. And so there is a much more energy required for vaporization than for fusion. And that's because in vaporization, you're going from liquid to gas, you're breaking all of the intermolecular forces. All of them are going away. It requires a lot more energy in order to do that. And so this is where we've talked about the idea that we use, like, say, cooling for vaporization, because there's a lot of energy that goes in. It's going to come from the surroundings. And so you're going to cool off, remove that energy, cause the temperature of the surroundings to decrease, but the temperature of, say, the water that's evaporating here doesn't change. Instead, it just becomes a gas. But whenever we're working through kind of more complicated problems of not just looking at, say, the temperature change of water, but temperature change of water and a phase change, we're going to need to put these kind of two different parts together. Let's look at an example. Application of warm water to crops can protect them from frost damage. An average orange can be protected by 65 grams of water at 25 degrees Celsius. How much energy is released when this much water fully freezes? So this is something that whenever there's like a freeze in Florida or in California or down in the lower Rio Grande Valley, where there's a lot of citrus grown, you'll get these images of, say, citrus fruit that are covered in ice because they sprayed water on them, right? On purpose, farmers put water on the citrus fruits. Why would they do that? And you'll see lots of reasons. I remember learning as a kid that, like, ice can't get below 0 Celsius. That's just wrong. And so all these sorts of things, but really it has to do with, it kind of makes sense if you just think about it. You spray warm water on them. So at a very bare minimum, you just spray warm water on stuff and it keeps it warm. But we can also see that the actual act of the ice freezing helps keep the orange warm. This isn't like a really permanent thing. This only works down if it like barely freezes, or you get to like -5, I think is the restriction, or -4 Celsius. So, but we'll at least be able to calculate this number. 65 grams of water, I calculated, that's about covering, I think it's like a millimeter of ice or something. If you cover the orange, that's how much heat. So we've got a lot of information that we're going to need. We're looking at freezing water. So we know we're going to be cooling off water. So I got some specific heat capacities. You will note they are different for the different phases. So we're going to need to consider that. I also have the delta H for the different phase changes. You'll note I have fusion and vaporization defined. That is a definition for going from solid to liquid and liquid to gas. So there's maybe some other phase changes we're going to use that we're going to have to modify these numbers and see how they work. So We'll get into this, but we'll use these numbers, but let's use our method of problem solving, kind of break down the problem, figure out what's going on. What do we want? What do we want? The energy is released when this much water fully freezes. So there's one of the things we know right away, joules or kilojoules are going to be our piece of information, and it's going to be energy released in this process. Okay, but you also note it's telling you what the process is. It's telling you that this water is fully freezing. So the question kind of would be, what does that take? So what other information do I have? I have 65 grams of water at 25 degrees Celsius. So this tells me how much water I'm using and what the starting temperature is. 25 degrees Celsius is like room temperature. So you took water from your house and you sprayed it all over your orange trees. How do I relate these? Well, what process is the water really undergoing? What is happening here? What is the water doing? And so this is where those tables are going to come into play, right? We know that the water is going to freeze. Okay, so I'm going to need to use fusion as my delta H. Fusion gives me the information, the delta H for solid to liquid, but I'm going the opposite direction. So that means I'm going to need a negative sign. And then the water has to cool before it can freeze. So I need to use the specific heat capacity of liquid water to see how much energy comes out, or do I have to take out in order to get from 25 degrees Celsius down to whatever the freezing point is, right? Water doesn't freeze at 25 degrees Celsius, so I have to cool off this water. This water is going to release heat into the oranges before it gets down to 0 degrees Celsius. So if I take this idea that I'm going to have two steps, I'm going to cool off the water and then I'm going to freeze it. And so if I want to think about what that looks like or where that would be, I know that first I cool off the water. I start at say 25 degrees Celsius and I cool it down to 0 degrees Celsius. Throughout that process, it stays liquid water and the only thing I change is temperature. Q is equal to mc delta T. Then the water will freeze once it gets down to that freezing point. And that is where I need to use the stoichiometry approach. Use those delta H, that delta H information that I had from the table for what the enthalpy for this phase change is. You'll note one of the ways we can think about it is you can only change one thing at a time. You either change the temperature or you change the phase. You cannot change both the temperature and the phase at the same time. Only one can change at a time. But we'll see how that looks. Kind of calculate out these two parts and add them together.
All right, so we want to know the energy that is released when this much water fully freezes. So we've already walked through the fact that the heat of the water is going to correspond to the heat from cooling plus the heat from actually freezing. Okay, we're going to change the temperature of the water, then it's going to freeze. So we'll do these one at a time, independent steps. So the cooling, because we're changing the temperature, that is mc delta T. That's going to be our standard equation for heating and cooling. So M is going to be 65 grams of water. The specific heat capacity C, there was those tables, 4.184 joules per gram degree Celsius. And then delta T is going to be the final temperature, 0 degrees Celsius, minus the initial temperature, 25 degrees Celsius. We are cooling down, going from 25 to 0. We can then just evaluate. This becomes negative 25, multiply everything out, and we get that the heat for cooling the water is negative 6,800 joules, which would be negative 6.8 kilojoules. And so we can see that negative sign implies that heat is leaving the water. So the heat associated with this process is negative because the liquid water is losing energy. It's in this case going into the orange, because that's why you put warm water on a cold orange, it warms the orange up. It cools up the water, the energy is flowing into the orange instead. So that's cooling. So now what about freezing? In this case, it's going to be an amount. Again, when we look up our value, we can see that delta H of fusion is equal to 6.01 kilojoules per mole. The thing is, fusion is solid to liquid. So what I'm interested in is liquid to solid, not melting, but freezing. So that tells me that delta H is going to be negative 6.01 kilojoules per mole. So it's still per mole. So I can take my 65 grams of water, use my molar mass, it's 18.2 for water. You can always calculate that yourself using the periodic table and the chemical formula. And then it's negative 6.01 kilojoules per 1 mole, which gets me negative 22 kilojoules. So then that tells me I know that Q of water is equal to the Q of cooling plus the Q of freezing. That is equal to negative 6.8 kilojoules plus negative 22 kilojoules, giving me negative 29 kilojoules. So we can use our two equations, the cooling of water and then the freezing of water. We can see that what's really going on here, why you spray water onto oranges to protect them, is that freezing of the water is exothermic, right? In order to melt, you have to put heat in. So when you freeze, when the water solidifies, it's releasing energy, and that energy is leaving the water, going into the surroundings, in this case, the orange. And there's a lot of energy, 22 kilojoules. So overall, you spray warm or room temperature water on cold stuff, that'll keep it warm. So you do get a decent chunk, about 7 kilojoules from that. So about a quarter of the total energy comes from just the fact that the water's already kind of warm. And then 3/4 of it comes from the actual act of freezing. That is an exothermic process that releases energy. It keeps the orange warm.
These same ideas about phase changes also apply when we do solid to gas phase changes. These are relatively less common, but we call it sublimation. That would be a solid to gas phase change. And deposition is gas to solid phase change. So those are our technical terms. And we can literally think about sublimation as the sum of fusion plus vaporization. Because basically, enthalpy is a state function. So you can take different steps. Either we can go solid to liquid to gas, so a 2-step process, or just solid to gas. So one of the things, sublimation always is endothermic. You're always going from solid to gas, and not only is it endothermic, it is exactly equal to the delta H for melting and then for the vaporization. So fusion plus vaporization equals sublimation. Deposition is just going to be the opposite process. And then it would be the sum of the negatives of the opposites of vaporization and fusion. So you just get the negative of that. And this is a really big energy change because in liquid, we think about breaking all of the intermolecular forces, but a solid has those intermolecular forces plus they're in like the perfect arrangement. So you're breaking all of that. A common case of sublimation, a common application is in dry ice, where that's solid carbon dioxide. And the reason why it's called dry is when it doesn't, think about cooling something with, water, ice, when it melts, it gets whatever you're trying to cool wet. So dry ice is really nice in that it just becomes gas phase carbon dioxide, which then doesn't get whatever you're shipping or whatever wet. You do make a lot of carbon dioxide gas, and what kind of functionally happens is it gets cold and makes water in the air condense, right? Because you've lowered the temperature, you hit that vapor pressure limit. So that's why you're seeing here, this is not, what you are seeing here is not carbon dioxide. What you're seeing is water that's in the carbon dioxide. And so, or in that kind of gas. And so that is still, there is some condensation, but still a lot better. But we can still understand the same things. It's all the same idea, undergoing that phase change. The temperature doesn't change, and then you would get sort of the change of the temperature using the different heat capacities for either the solid or the gas. Okay, got our first question for participation 9-1. Plenty more videos to go. Trying to finish chapter 10 here, looking for more questions for participation 9-1. See you in the next video.